Okay, lecture 5, wave properties of light 2. Lecture on online classes, course code EE4233, course name Optoelectronics. At the end of this class, we would be able to learn what is a Snell's law and its importance, principle of Fresnel's equation, mathematical derivation related to Snell's law and Fresnel's equation, and the total internal reflection or TIR. So this is Snell's law or Descartes' law, it can be called also. The left side figure is the Snell one, and the right side figure is the Drain-Riggers. We know Snell's law previously in HC, or I think in SSC also. So what happens here? There is a two medium N1, medium N2, where N1 is denser than medium N2. So if a light incident occurs, if we see here, we know this equation earlier. If a light incident occurs here in this medium N1 to N2, then some part of the light would be reflected and some part of the light would be transmitted. And according to the Snell, this is the equation that represents Snell's law. Now, the derivation of the Snell's law. Here we are seeing a light wave traveling in a medium with a greater refractive index, N1 is higher than N2, suffers a reflection and refraction at the boundary. Note that the lambda 1, which is this one, is slightly shorter than the lambda. So lambda 1 is slightly longer than lambda. These two wavelengths are going here. Here we can see that this A1 to A prime, this wavelength is going through A to A prime in N2 medium, and this wave at that point when it is in B position, it goes from B to B prime in N1 medium. So when deriving Snell's law, we should consider this concept. We can use constructive interference to show that there can only be one reflected wave which occurs at an angle equal to the incident angle. The two waves along AI and BI are in phase. When these waves are reflected to become waves AR BR, then they must be still in phase, otherwise there will be interfere destructively and destroy each other. The only way the two waves can stay in phase if theta r equals to theta I. All other angles lead to the wave AR BR being out of phase and interfering destructively. Using the two waves at A prime B prime, still they have in same phase, there will be no transmitted wave. A prime B prime points on the front are only in phase for a particular transmitted angle theta t. It takes time t for the phase at B on the wave BI to reach B prime. So we can know that S equals to ut. So VB prime equals to V1t, where V1, which is the velocity of the wave that was in medium N1, so we can write down Ct divided by N1. And for during the time t at the phase A, which has progressed to A prime, we're getting A prime equals to V2t, V2 which is the medium velocity for N2 medium, so we can get Ct divided by N2. A prime and B prime belongs to the same front, just like A and B, so that AB is perpendicular to Ki in the medium 1 and A prime B prime is perpendicular to the Kt in medium 2, where K are the group velocities. So considering geometrical consideration, we are getting these equations: AB prime equals to BB prime divided by sine theta I, and AB prime equals to A prime divided by sine theta I, so that our AB prime becomes V1t divided by sine theta I, which is equals to V2t divided by sine theta t. Sine theta I and sine theta t ratio becomes N2 by N1. So this is the final Snell's equation or Snell's law. So it relates with the angle of incident and refraction to the refractive index of the medium. So angle of incident and refraction to the refractive index of the media can be shown by Snell's law. So in the exam, if there is a derivation for the Snell's law, you have to write down from the previous slides to up to here. So when n1 is greater than n2, then obviously the transmitted angle is greater than the incident angle as appeared in that previous figure. When the refractive angle theta t refraction angle reaches 90 degree, the incident angle is called the critical angle, which is theta c, which is given here, sin theta c equals to n2 by n1. When the incident angle theta I exceeds theta c, then there is no transmitted wave but there is deflected wave. Now, this later process is called total internal reflection, or TIR. TIR is phenomena that leads to the propagation of waves in a dielectric medium surrounded by a medium of smaller refractive index in an optical guide or optical waveguide. For example, optical fibers. Although Snell's law for theta I is greater than theta c shows that sin theta c or sin theta t is greater than 1, hence theta t is an imaginary angle of refraction, and then however alternated wave called the evanescent wave. This is a pictorial diagram of a total internal reflection. We can see from this figure that when the incident angle has a higher angle than the theta c, we are getting a reflected wave. The light wave traveling in more dense medium strikes a less dense medium depending on the incident angle with respect to theta c, which is determined by the ratio of refractive indices. The wave may be transmitted or reflected when theta I is greater than theta c. Here we can see this figure. This is when theta I is less than theta c. This is when theta I and theta c are both same, and this is when total internal reflectance occurs when theta I is greater than theta c. So incident angle is greater than critical angle, then the light would be reflected. This is a figure of a prism. This is a refracting prism and this one is a reflecting prism. So in this prism, basically what happens, the light makes a TIR, but in this prism there is no TIR. Now we can see the light, how light travels through a total internal reflectance in optical fiber. This is a schematic diagram where the information is been passed through the digital signal, then an emitter which is gone through the optical fiber, and then the output has been detected by the photodetector and the information comes. So inside that optical fiber, what happens? The fiber core has a higher refractive index so that the light travels along the fiber into the fiber core by a total internal reflectance at the core cladding interface. So there is a lot of TIR happens here within the fiber where N1 is greater than N2. So there are always a TIR, and this is how the light signal passes through the optical fiber and gets the output. So Fano or Fanel's equation. So Fanel's equation is basically when light wave traveling a more denser medium strikes a less denser medium. The plane of incident in the plane of the paper and is perpendicular to the flat interface between the two media. The electric field is normal to the direction of the propagation. It can resolve into perpendicular and parallel component. So all electric field has two components. One is parallel to the direction, another one is perpendicular to the direction. So there is incident wave, there is transmitted wave, and there is reflected wave. Each wave has two components, one parallel to the direction, another one is perpendicular to the direction. So using this concept, we are using the Fanel's equation. There are some boundary conditions in the Fanel's equation which will be described later on. So incident, reflected and refracted wave by the exponential representation of a traveling wave is shown here, where EI represents the incident wave, ER represents the refractive wave, and ET represents transmitted wave. All these waves are traveling wave. Here, the R is the position vector, and the wave vector Ki, Kr, and Kt describes the direction of the incident, reflected, and transmitted wave. EI0, ER0, T0 are the respective amplitudes. Any phase change such as phi R or phi T in the reflected or transmitted wave with respect to the phase of the incident wave are incorporated into the complex amplitude, which is ER0 and ET0. Our objective is to find ER0 and ET0 with respect to the EI. The electric and magnetic field anywhere on the wave must be perpendicular to each other as a requirement of electromagnetic wave theory. This means that with E parallel in the EM wave, we have a magnetic field B perpendicular associated with it such that B perpendicular equals to N by C E parallel. So similarly, E parallel rather E perpendicular have a magnetic field of B parallel associated in such a way that B parallel equals to N by C E perpendicular. So using this boundary condition at E tangential point, there are continuity. So E tangential equals to at medium 1 is equals to the E tangential at medium 2. Also monomagnetic media where refractive index is mu r equals to 1, we are getting B tangential 1 which has a continuity towards the B tangential 2. Using this boundary condition for the field y equals to 0 and the relationship between the electric and magnetic field, we can find the reflective and transmitted wave in terms of incident wave. The boundary conditions can only be satisfied if the deflection and incident angles are equal, that is theta r equals to theta I, and the angle for the transmitted and incident wave obey Snell's law, which is n1 theta 1 equals to n2 theta 2. So here is a figure for the Fresnel's equation. These are the incident wave where two waves are showing here. One is theta I when incident wave is smaller than theta c, and when incident wave is greater than theta c. So what happens here, applying the boundary condition to the EM wave going from medium 1 to medium 2, the amplitudes of the reflected and the transmitted wave can be readily obtained in terms of n1, n2 and the incident angle theta I. These relationships are called Fresnel's equation. If we define n equals to n2 by n1 as the relative refractive index of medium 2 to that medium 1, then the reflection and transmission coefficient for E perpendicular are, so these are the equation for R perpendicular. So this equation is for R perpendicular, and for mathematical problem to solve, these equations are important. So this one is for T perpendicular. So the transmission perpendicular equation, there are corresponding coefficients for E parallel field with corresponding reflection and transmission coefficient R parallel and T parallel. So this is an equation for R parallel and this is an equation for T parallel. So the derivation of this equation is not needed for this course. It is for the intermediate courses. From now on, we will use these four equations to solve the mathematical problem. The derivation is out of contest for this course. Further, the above coefficients are related by R parallel plus N T parallel equals to 1 and R perpendicular plus 1 equals to T perpendicular. So from there we can see that for normal incident when theta I is greater than 0, the Fresnel's equation R parallel and R perpendicular are same, and that is n1 minus n2 divided by n1 plus n2 for normal incidents. And this is a figure which can be shown here that like magnitude of the reflective coefficients are parallel and are perpendicular versus the angle of incident when ni is greater than n2. So this is an internal reflection, if I say, where ni is greater than n2. Here we can see this figure that the angle of reflection coefficient comes to 0 when theta p, and for a parallel reflection and for perpendicular we see that for perpendicular the angle of reflection becomes higher when it comes to theta c, which is the critical angle. It becomes reflective and it becomes 1, which is very much physically reliable. On the other hand, we see that the phase becomes 0 until the critical angle comes, and after the critical angle the phase becomes 180 degree, and there is we have getting TIR. And in case of parallel, we are getting an angle where the reflection is 0, and after that from here to here the reflection angle or reflection coefficient becomes higher and then it comes 1. So when we are going to solve a mathematical problem related to these equations, the picture will be clear for us. So that's the end of this lecture. Thank you, and if you have any query about this lecture, please note down and show it in the upcoming Zoom live classes. uh, there will be some mathematical problem related to this class, so focus on the mathematical problem uh, for this lecture, rather derivation. Thank you.